Hello everyone, my name is Vibin Abram and in today's video we are going to talk about electric field. We will talk about how is this electric field came into existence. Right. So basically we know that whenever we have any two charge, let me call it Q1, another charge to be Q2 and they are separated by some distance R, then by Coulomb's law we know that they are going to experience a force of interaction which will be simply given as F is equals to K Q1 Q2 upon R square. Now this is something which we have already studied. Let's for a time being assume that instead of 2 point charges, let's say I have a single charge, right? Okay, so let's assume for a time being that I have only single charge Q. Alright, so when you have single charge Q, the single charge Q, let's say there is no other charge in its vicinity, definitely the single charge Q will not experience any kind of force of interaction, right? Okay, now let's bring a charge Q1 into its vicinity, right? Okay, let me bring a charge Q1 over here. Now this is a charge Q1, I brought it over here, right? The moment I bring this charge Q1, this Q1 charge is going to experience a force of interaction in that direction. So let me call it force on Q1 because of capital Q. Very similarly, this capital Q will also experience a force of interaction, that is force of interaction on Q because of Q1 charge. Yes or no, right? Okay, great. Now let's remove this charge. The moment I remove this charge, the force of interaction will also go, right? So the force of interaction on the charge Q will also go, right? Okay, that's fine, that's fair. Okay, now let's bring the same Q1 charge at some other position, right? Okay, right, the moment I put my Q1 charge on that position, again it is going to experience a force of interaction, force on Q1 because of capital Q. Very similarly, this will also experience a force on Q because of Q1, right? Again, I bought this Q1 charge at a different position, but again the force of interaction came the moment I kept my charge in its vicinity, right? Great. Okay, let's for time being erase that too, right? So I have erased it. The moment I erased it, the force of interaction will also gone, right? Now okay, let me place Q1 at some different position now, right? Different than the first and the second, right? Again, when I put this at different position, again this Q1 charge is going to experience a force, that is FQ1 because of capital Q. Very similarly, this capital Q will also experience force on capital Q because of Q1. Again, the moment you place the charge, the force emerged, the force just came from somewhere, right? Great, I hope you guys are following this, right? Very similarly, okay, let me erase this one also. The moment I erase it, the force of interaction will also go, right? Now let me place this at some different position than the first three, right? Okay, let me place it at this position. The moment I place my Q1 here, again this Q1 is going to experience a force FQ1 because of capital Q. Very similar, this capital Q will also experience a force FQ because of Q1, right? So basically what we have seen in this experiment is that I placed a different charge, or I should say the same charge, at different places, right? Again, the moment I place my charge, the force come all of a sudden, right? So I place my charge Q1 here, the force came, right? When I placed it here, the force came. When I placed it here, the force came, right? So the important conclusion that I can draw from here is, okay, obviously the forces were in different direction, that depends upon where the charges are placed, that is completely understandable from Coulomb's law, but still the important conclusion that we can make from this experiment is, the moment I place my second charge, the force came rushing through, right? The moment the charge is placed, the force is experienced. Now this was very peculiar phenomena, right? So the force will only experience the moment you place the charge, Now that is something which is very abrupt, right? You cannot explain that, right? So in order to explain this, what scientists at that time thought, they introduced this concept of field. Okay, so let's try to understand this. So scientists introduced the concept of field, right? They said that the charge q produces an electric field. Okay, now they said, okay, there is this charge q that we just saw, it produces some kind of field which they call it electric field, right? Which is invisible. Important, it is invisible, you cannot see it from your naked eye, right? Invisible electric field everywhere, okay, in the surrounding. And when another charge q or q1, whatever you call it, is brought at some point p, okay, let's say they were brought at some distance p from the capital Q, the field there acts on it and produces a force. So they said, okay, let me just draw it. Okay, so I have this capital Q. So they said this capital Q is producing electric field in its surrounding in all the direction, right? So let me say, okay, some kind of, now I have drawn it like that, but remember these are invisible electric fields, right? So the scientists said, okay, there is some invisible electric field which is like flowing everywhere in every possible direction from this capital Q, right? Such that the moment, let's say there is one electric field in this direction, right? The moment, let me use different pen, the moment I place a q1 charge, the moment I place a q1 charge, right, at some point p, right, let's say this, let me call this point as p, at some point p, because of this field, this q1 charge is going to experience a force. Make sense, right? Very similarly, if I place my q1 charge, yes, because of the field it is going to experience a force, right? Again, I place it over here, because the field is going to experience a force, right? I place it over here, because of the field it is going to experience a force, right? So they said that there is a invisible electric field around this q charge, such that the moment you place another charge in its vicinity, it is going to experience a force because of the field, right? I hope whatever I'm saying making sense to you, right? Okay, now we understood, okay, there is some kind of invisible field around this capital Q charge. Now my question is, how can you find out the value or the strength of electric field? Now let's try to understand what actually is electric field. Is it a vector quantity, is it a scalar quantity, or it is some quantity which helps us to understand what this force is acting? Let's try to find out, right? Okay, so the question comes that how to find out electric field at a point, right? So you want to find out now you want to find out that how you can actually find out the value of electric field, which we just learned how to find out this value, right? Okay, so again it is defined in such way, right? So it is defined as the force experienced by unit positive charge placed at any point P. Now let's try to understand this. Let me draw it, and you guys will understand. So they are saying, let's say I have this charge Q, right? I have this charge Q, and we have just we have just understood that there is some kind of invisible field from this plus Q charge, right? No, it's a positive charge, plus Q charge, right? Okay, so according to this definition, it is defined as the force experienced by unit positive charge. So let's say you bring a unit positive charge, I'll call it test charge. We normally call it test charge, right? I'll make you guys understand what this is, right? Just wait a minute. Test charge. So you have brought a test charge. Now there are few properties of this test charge. This test charge is it is so small that you call it vanishingly small, right? The value of the charge is very, very small, that is least possible, right? Now why is that? Why you take your test charge to be very small, so small? It is because I do not want, because whatever charge you're going to bring, the charge itself will have its own field, right? Now you call it test charge, and you said that the magnitude of this charge is going to be very, very small, because you don't want to disturb the field of your actual charge. Because let's say you brought a very strong charge, what is going to happen? This strong charge, let's say you brought this is a strong charge, right? So the moment you brought a strong charge, what is going to happen? This strong charge is going to disturb the field of the charge which we want to find out, right? So because of this reason, we just say that our field or our test charge should be vanishingly small, right? That is the first thing, that your test charge must be vanishingly small, right? The magnitude should be vanishingly small, right? The second property is it is always taken positive. It is always taken to be positive. These are the rules, you have to follow it, right? The test charge is vanishing, the magnitude of the test charge is vanishingly small. The second thing is that the test charge should be positive, right? I hope that's understand, right? So according to our definition, right, now this q charge is going to let's say this is my point P, right? This is my point P, let me call it point P, right? Okay, so this q charge is going to there will be field in its surrounding in all possible direction, right? Okay, now field will be in that direction also, and because of this field, this test charge q naught is going to experience a force. Let me call that force to be F, right? This test charge is going to experience a force which is actually F. Now how you are going to define electric field? Electric field in mathematical terms, let me write it down, it is defined as force experienced by that test charge, the force experienced by that test charge per unit charge that has been used to find out the electric field, right? And you call it limit q naught tends to 0. Now why I have written q naught tends to 0? Because your q naught must be vanishingly small, right? So this is how you will mathematically write it, right? Let me try to do it again. I'm saying electric field is defined as the force experienced by the unit positive charge placed at any point P in its vicinity, right? So you guys can see there was this q charge was here, and my q naught was placed over here, right? So this q naught, because of the field, experienced a force F, a repulsive force. So you can simply say electric field is defined as how much that force that is experienced by that q naught divided by the charge q naught. This is how you define your electric field at any point, right? Let's say I'll try to see in the next slide, we will try to understand that more, right? So basically what I'm trying to say over here is that your electric field is actually the force experienced by the unit positive charge or the test charge divided by the test charge itself. That is how you define your electric field. I hope that is understandable, right? Okay, right. So limit q naught tends to 0. So why I'm writing q? Because you want your q naught to be as small as 0. It should be tending to 0. That's why I've written it mathematic, right? I hope that is understandable, right? So in normal terms, you can actually take it, the limit q naught tends to 0, you can omit that and simply you can write F upon q naught. That is also fine. E is equals to F upon q naught. This is the formula that we are going to use in our coming videos, right? I hope that is understandable, right? Great. Okay, if that is understandable, now we have to see whether your electric field is it a scalar quantity or a vector quantity. I'm sure you guys can see this vector sign over here, so I'm sure you must have guessed it that your E is actually a vector quantity, right? Electric field is represented by E and it is actually a vector quantity, not a scalar quantity, right? So you guys can see E is written as force experienced by the unit positive test charge divided by the test charge itself, right? So E is supposed to have a direction too, right? And you guys can see E will have the same direction as that of force, because you guys can see E is equals to F upon Q naught, right? So F is the only vector quantity here, Q naught is a scalar quantity, right? So whatever direction is the force will be having the same direction of E, right? So in whichever direction the force is going, electric field will be in that direction too. For example, let's say I have this charge Q, right, and I have to find out at some, let's say at this point P, I want to find out the electric field of this charge Q. How will I find out? Simply, I will place my test charge here. I will bring a test charge Q naught and place it at Q, right? Now the moment I place it at Q, it is going to experience a force in that direction. Yes or no? Force on Q naught because of Q, right? Now direction of force I know. Very simply I will say, okay, that is the same direction of the electric field. Electric field is going in that direction. I hope that is understandable, right? So what we learned, that electric field, your electric field E is a vector quantity, right? And very simply, if somebody asks you what is the SI unit of electric field, it's simple. Electric field is given as F upon Q, right? F upon Q naught, right? So F has a unit of Newton, Q naught has a unit of Coulomb, so Newton per Coulomb is the SI unit of electric field, right? I hope that is understandable. Newton per Coulomb. You can also find out the dimension formula. I'm sure you guys can do that, right? Okay, let's move to the important part. Electric field at a point due to a point charge Q. Now let's try to find out mathematically how you can do it, right? Let's say I have a Q charge, right? I have a Q charge, and obviously we all know this Q charge is going to is going to produce electric field in on all possible direction. Now let's say there is some point P over here, which is some distance r from my Q charge, and I'm supposed to find out electric field at that point. How will I find it? Very simple. You will place a Q naught or a test charge, unit positive charge. You'll bring it over here, you put it over here, right? Ekdam se you'll just put it over there, right? The moment you bring the Q naught charge there, right, the Q naught charge is going to experience a force, electrostatic force, right? So it is going to experience a force on Q naught because of Q, right? So we are going to find out the value of that force, right? So that is that force, the value of force, we all know the value of that force will be Q naught. Q is equals to K Q naught upon R square, right? The main thing that we are going to find out over here is what will be the value of electric field at this point because of Q charge, right? Yes or no, right? So we know our electric field at any point is defined as force experienced by the unit positive charge divided by the charge itself, right? So I know this Q naught Q force, this is the force experienced by the unit charge. Yes or no? All you have to do is place it over here. So your electric field will be equal to, yes, this will be equal to K Q naught upon R square divided by Q naught upon 1, right? Or simply you can write it K Q naught upon R square into 1 upon Q naught, right? Q naught will cancel out, so your electric field will be simply given as K Q by R square, and the direction will be let me call this A and B, right? Direction will be A to B, right? Or sorry, the P part, A to P will be the right answer, right? This will be A to P, right? I hope that is understandable, right? So very simply, if somebody asks you, right, so what does this mean? This means that if you have a Q charge and you're supposed to find out electric field at some point P r distance away, then it is simply given as what? It's simply given as electric field is simply given as K Q upon R square, and it is actually away from it, right? I hope that makes sense, right? Okay, now let's say I have a charge q and I have at this point p, right, and which is at, let's say, r by 2 distance, right? So what will be the electric field? Electric field will be simply equal to k q upon r by 2 whole square, and this will be equals to k q upon r square upon 4, right? I hope that's understandable, right? So this will be 4k q upon r square. I hope I'm making sense, right? I hope that's understandable, right? That's how you will find out electric field at different positions, right? Okay, now one thing is very clear, that if you have a positive charge plus q, then I'm very sure the electric field is going away. Electric field is going away in that particular, in every possible direction, yes or no? Now let's say you're supposed to find out electric field because of a negative charge, right? So how will you do it? It's very simple. You'll place, let's say you want to, you want to find out electric field at some point p, right, which is some distance r away from it, right? So definitely the trick is you will bring a q0 charge, a q0 test charge, positive test charge at that place. The moment you bring the positive test charge, what is going to happen? This charge is going to experience a force, but this time, because it's negative charge, the force will be attractive rather repulsive, right? So this will be the force on q0 because of minus q charge, right? So electric field will be given as, very simple, right? Electric field will be given as k q upon r square, but this time the direction will be opposed, right? Direction will be opposed, right? Direction will be, let me call it a, right, from p to a, right? So that means if you have negative charge, the electric field is attractive. The electric field is attractive. If you have negative charge, the electric field is attractive in nature, right? I hope this is understandable to everyone, right? So I hope you understood the whole mechanism of electric field, right, from the start and to that point where you can actually feel it, that okay, this is how you calculate the electric field, right? So if you have any doubt, you can ask me in the comment section, and I hope you understood the video, right? So if you did, do like it, do subscribe to it, right? So that's all for today. I hope all of you are doing good. Have a nice day.